One of the biggest challenges that we face in calculus is our basic algebra skills. And algebra is really important, so I want to take a few minutes, hopefully not too many, to just do some review of ideas that come from algebra. And so when I'm talking about algebra, I'm really talking about this ability to manipulate expressions with a goal to simplify or solve something. So simplifying is good. We want things to be simple. And also solving is good because we want to know the answers. That's oftentimes what we're after. Now, one of the things you're going to see as we talk is there's an interesting interplay between addition and multiplication. And you've got to understand it, that these behave very differently and they don't always mix well together. So we're going to do a couple of things here. But let's just start by talking about foiling. So foiling is something you may have heard of, and the idea comes from first, outer, inner, last. But really the principle is the following. Suppose I have two things multiplying together. Let's say A plus B and C plus D. Then what to do is when we multiply these together, we want to get all possible combinations. So in other words, I'm going to pick something from the first term and something from the second term. So I could pick A and C. So I get AC. Or I could pick A and D. So that's A and D. Or I could have picked B and C. So that's B, C. Or I could have picked B and D. That's B, D. Whoops. All right, well, that's the same as DB. Order of multiplication doesn't matter. But notice here, you get the first terms, the outer terms, the inner terms, and the last terms. That's where the word FOIL comes from. But what's the real principle? The real principle says if we're multiplying things together, you pick one from each in all possible ways. In other words, if there's 2 here and 2 there, well, then you pick one. There's 2 choices, 2 choices, you end up with 4. And of course, you can imagine if there's more, well, lots can happen. So you could have A plus B plus C times D plus E. And well, how many terms will we get? Well, 3 to pick, or 2 to pick. 3 times 2 gives you 6. So you get AD plus AE, and so forth and so on. Now, one of the things that we should note is that parentheses matter. Parentheses matter. So pay attention to your parentheses. In other words, if you don't pay attention and you just drop them, then you might accidentally lose some meaning in your expression. So what do we mean? Well, compare the expression x squared plus 2 times x versus x squared plus 2x. You'll notice all the symbols are the same. The only difference is here we have parentheses. There's no parentheses. Are these the same? And the answer is they're not the same. Why? Well, notice here that the x would distribute into both terms. So you're really going to have x cubed plus 2x, not x squared plus 2x. So remember that the x distributes through. Oftentimes, when people make mistakes, one of the most common things is they forget parentheses, or they write parentheses down and they say, I don't need to bother, and so they don't multiply them through. Another common thing is the minus sign in front of parentheses. So minus x minus 3. Well, it's tempting to say, minus x minus 3. Just drop the parentheses. But it's not right. See, this minus sign has to distribute. So, yes, you will get a minus x, but then you'll get a minus minus 3. So you should get minus x plus 3. So pay attention. Pay attention. We don't want to lose any points. Our goal is to get all the points. All of our points. All right. Well, something else that you might encounter at some point in time is adding fractions. Now, one of the things is we'd like to have things simplify in a nice way. So, what's nice? Well, it would be nice if I had A over C, plus b over d, and I just said, oh, I know, I'll just add the tops. Except it doesn't work. To convince yourself, let's just try an example. A half plus a half. If I added the tops together, well, that'd be 2 because 1 plus 1. If I added the bottoms, that'd be 4. And 2 over 4 is a half. Well, does a half plus a half equal a half? And the answer is no. They don't equal each other. So what do you do? So when you're dealing with fractions, one important thing is to look for a common denominator. All right, well, what does that mean? Here, the denominators are c and d. So I want to get something which is the same for both. So an easy way to do that is to multiply c times d. So I can say, okay, well, what do I need? If I have c already, I just need to get a d. So I could multiply top and bottom by 1. And here I need to get an extra c downstairs. So I multiply top and bottom by c. And lo and behold, we get AD plus CB, and now our denominators are the same, and we can put things together. Life is good. Life is good. All right. So, on a small side note, let's see, there's space here. There's space here. One of the mistakes that we occasionally encounter, and, well, of course, you are a good student. You're going to make these mistakes. But, you know, maybe your friends will. So we'll talk about a mistake that we sometimes see. So one of the mistakes we sometimes encounter is people say, aha, I have x plus 3 over x squared plus 4, and I know that that's x over x squared plus 4 and 3 over x squared plus 4. In other words, I can break up addition upstairs. And that's not a mistake. That's not the mistake yet. I'm sorry if I made you think that was a mistake. That's good. So addition in the numerator is fantastic. And that's essentially what's happening here. We said, okay, look, we really have addition in the numerator, which allows us to break things apart or combine them together. Now, this is good. So we should put a smiley face. Yes, good thing. So, what's bad? Well, something else that you might be tempted to say is, well, what if I had x plus 3 over x squared plus 4, and we wrote that as x plus 3 over x squared plus 3. Sorry, x plus 3 over 4. In other words, break up addition downstairs. This does not work. You can't break up addition downstairs. So if you have a fraction and you want to break things up, break it up upstairs, perfect. Bring it up downstairs, no good. Now you might say, but wait a second, what if I have something downstairs and I really, really need to break it up? I need to pull it apart. Is there any way to do that? And the answer is yes. There is a great way to do that. It's called partial fractions. And we'll talk a little bit about that in the Calc 2 course. And so if you need it, in Calc 2, we'll see it then. All right. So let's move on to something a little different. Well, maybe a little bit more with fractions first. All right. So let's do a quick example. Suppose I have 2 over x plus 2, and I want to add 1 over x. You'll notice that now these aren't numbers. These are functions. These are expressions with x. Are we still allowed to get a common denominator and add things together? And the answer is yes, we can. It's fine. It's perfectly fine. Now, what do we get? Well, common denominator would be multiplying those things together. So I get 2x over x plus 2 times x. So notice the x is multiplied both top and bottom. It's essentially multiplying by 1 in that I multiplied by 1. All right, and now the second term, I multiply by x plus 2 on top and bottom. So x plus 2 times x. Now the denominators are the same, so we get at the end, downstairs x plus 2 times x, upstairs 2x plus x plus 2, also known as 3x plus 2. Now, one other quick thing to note here. One of the mistakes that we sometimes see is if you have an expression like 2 over x plus 2, you're like, hey look, there's 2's, I can cancel the 2's. So there's a desire to say this is the same as 1 over x plus 1. However, this is not the same. Be careful. Well, what's wrong here? Well, what's wrong here is you can't pick which parts of things that are being added together to cancel. You either have to do it to all of them or to none of them. So I can't just cancel off the 2 willy-nilly. I have to be careful. I have to be consistent. Consistent is important. All right. Now another related type of operation that you'll sometimes encounter is that of what's called conjugation. So conjugation is a very fancy way of saying we're going to take an expression and change the sign in the middle. Now that might not seem like very much, but in some cases it can help. So you might be faced with an expression like the following: 1 over square root x squared plus 1 minus x. All right, so what does conjugation say? Well, it says if you have two things and you change the sign in the middle. So in our case, well, it'll be square root of x squared plus 1 plus x. And the idea of conjugation is multiplying by the conjugate. Square root of x squared plus 1 plus x. And square root of x squared plus 1 plus x. Now, here's a nice idea. In this one, it's important for us to pause and say, hey, that's a nice idea. Notice this is multiply by 1. And multiply by 1 is a good thing. We like to multiply by 1. Because if you multiply something by 1, you haven't changed its value. Now, an alternative which you will sometimes see is also add by 0. Again, add by 0, great thing. If you can do that, then do it. Now, of course, you don't multiply by any 1, and you don't add just any 0. You always choose a nice 1 or a nice 0. Now, what do we mean by nice? Well, nice is a fancy way of saying something that helps to simplify what you're working on. Now, in this case, the conjugate actually is nice. Because what happens? Well, upstairs, 1 times that part, and remember, it's times the whole thing. So that would give us square root of x squared plus 1 plus x. And downstairs, well, square root of x squared plus 1 times square root of x squared plus 1. That would produce x squared plus 1. Then we have plus x, square root of x squared plus 1. Oh, my God, it's getting longer. Minus x squared of x squared plus 1. And then minus x plus x is minus x squared. But the nice thing is those terms cancel. In fact, it looks like it's really nice. X squared minus x squared. This is a case where conjugation helps tremendously. We're only left with 1 downstairs, which means you get a final answer of the square root of x squared plus 1 plus x. Nice. Nice. Good. So conjugation can be very, very helpful. Now, one of the things that we can see here is that there's really a special pattern here. This is a very famous pattern, so it's one of those ones that you should know. Know by heart. If you have x plus something, and of course, it doesn't have to be x, it could be any symbol that you want, and x minus something. So x plus a, x minus a, that is x squared minus a squared. What happens is you get the cancellation like you did over here. This is very, very common. You should be able to recognize when you see expressions and jump back and forth. Now, sometimes, of course, they make this x squared minus a squared a little bit hidden. So what do we mean? Well, maybe they'll write something like, well, let's say x to the 6 minus 1. And you're like, oh, well, that's not a difference of squares, because that's not a square, it's a 6th power. But you can rewrite it. That's x cubed squared minus 1 squared. And we say, ah, so it is a difference of squares. So it's x cubed minus 1, x cubed plus 1. All right. So that's good to know. Now, some other expressions is actually squares. X plus a squared, which by that we mean x plus a times x plus a, which is x squared plus 2ax plus a squared. Or we can take x minus a squared, which is x minus a times x minus a. And that's almost identical, except the middle now becomes minus, because you'll see it's minus ax. And the stand is still plus a squared. Again, this x squared plus 2ax plus a squared, you will see it again and again. So you just want to get to the point where it's like, aha, that's a perfect square. And perfect squares are our friends. Because in many cases we have to learn how to handle a square root. And oftentimes the best way to handle a square root is to get rid of it by using things like perfect squares. All right, well, so one of the things that we can do is a process called completing the square. Now, what does that mean? Well, it means that we have a couple of terms, so we sort of have something starting out, and we want to make it a full square. So, maybe I have x squared plus, I don't know, let's say, right now I'll do bx in general. We'll do some specific examples in just a moment. So what do I want? I want to add something here so that the end result is a square. Now it's not so hard to figure out because we know what a square should look like. We know it should be x squared plus 2ax plus a squared, because that's our square. So okay, so if we look, here we have b and 2a, they have to match up. So I can say, that really says a better be a half b. So a squared better be 1/4 b squared. And if we do that, now we say, lo and behold, this is x plus a half b quantity squared. Now there's a couple of things to be careful about. One of the things to be careful about is make sure there's a 1 here. So if there's not a 1 there, make it a 1, and you can make it a 1 by factoring things out. The other thing to be careful about is make sure when you manipulate your expression, if you put something in, you take something out. So let's do a quick example. Suppose I wanted to talk about 4x squared plus 10x. I want to say, well, what does that become? Well, I can't just take the 10 and divide by 2 because this is not a 1. So, first thing is, let's pull the 4 out. So that's x squared plus, now 10 divided by 4, 5/2 x. And leave ourselves a very big gap. All right? Well, why a big gap? Well, now we're going to do our trick. Our trick says take this middle term, divide it in half, and square it. So here I have 5/2. Divide in half, that's 5/4. And if you square 5/4, that'll give you 25/16. That's a perfect square. But I've now added something in. I have to find a balance. So this gets back to our add by 0. So if I add 25/16, we subtract 25/16. And lo and behold, what do we get? Well, this becomes, the first part is x plus 5/4 squared. Then we have the 4. So I put the 4. And now, remember, the 4 comes through. So the 4 multiplied into the first 3 terms gave us that. Now the 4 onto the last term, I can cancel off 4 into the denominator, so we get minus 25/4. And there's our expression. There we go. Complete the square. Good. All right. Well, oh my goodness. This paper is bleeding through a lot. That's okay. No problem. Paper is great. It grows on trees. We have plenty of paper. Now, another thing that we might want to deal with is factoring. So what is that? Well, the goal of factoring is sort of the opposite of expanding. So we did an example near the start where we expanded terms out. Now we want to put them back together. Now why do we want to factor? Well, one of our goals is to find the roots. In other words, I have something. Usually we're going to restrict ourselves basically to quadratics. And if we need to, we can find the roots. Now, in the back of our mind, we always have the following. If I ever see something with ax squared plus bx plus c equals 0, I can always find the roots by using the quadratic formula, which says that x should be negative b plus or minus the square root b squared minus 4ac all over 2a. Now, can you use this? Yes, absolutely. And once or twice you might even need to use this. But this should be sort of a last resort. Only if you can't see what to do with factoring do we resort to the quadratic equation. Because oftentimes what we're dealing with is a much simpler thing to work with. And so we'll try something else. Now in general, what do we have? Well, we have the following. If we have something of the form x squared, and I'll just make it a 1 for now. You can always make it a 1 by factoring now. Plus bx plus c. Well, this c, that comes from multiplying. So in other words, I want to find two things that multiply together to get c. And for b, that comes from add. I want to add two things together and get b. So let's try some examples. X squared plus 5x plus 6. All right, what could that be? Well, I need two things that multiply to 6. Well, 6, there's not a lot of ways to write 6 as a product of two nice numbers. Now, there's lots of ways to write 6 as a product of not nice numbers, but two nice numbers, there's like 1 and 6, and 2 and 3. So I'm looking for some combination. Now, see that this is a plus. I want them to be the same sign, and because, they have to either be positive, positive, or negative, negative, because this is also plus positive, positive. So I'm looking for two things that add together to give 5. 2 and 3. Perfect. So that says this becomes x plus 2 times x plus 3. Now, on the other hand, I could have something like this. X squared minus x minus 6. All right, now what do we do? Well, let's think about it. What do we need? We need to have two numbers. Now, notice the minus 6. So that says they can't have the same sign. They have to have opposite sign. So it's going to be 3 and 2, but one of them would be negative and one of them would be positive, or it's going to be 6 and 1, but one would be negative, one would be positive. All right. Now, when I add them together, I need to get a negative. So that means the larger number better be negative. So if I have 2 and 3, if I make the 3 the negative and the 2 positive, let's check. It'd be plus 2 and minus 3, minus 1, and negative 6. Perfect. Perfect. X plus 2, x minus 3. All right. What if it was x squared minus 5x minus 6? Well, now what happens? Well, again, you have to have a different sign, and I have to have them so that I get a negative 5. Well, in this case, if I make it negative 6 plus 1, well, they multiply to negative 6 and add to negative 5. So it would be plus 1, x plus 1, and x minus 6. All right, so get practice with factoring. A lot of problems will factor, not because factoring is actually that common, but because we like nice problems. And so you'll see that happening frequently. All right, now one of the things that we might have to do before we factor is to simplify our expression. So maybe we have something like this. 4 over 3x plus 8 over 3x squared minus 4 over x cubed. And we want to say, well, is this factor? I mean, what does that even mean? Well, one of the things to do is to say, okay, well, let's think about what's going on here. First thing is the x's, we can rewrite that as negative powers. So I can say this is 4 thirds x to the negative 1 plus 8 thirds x to the negative 2 and minus 4 x to the negative 3. And now when you have an expression like this, one of the things you should say is factor out what's in common. So we're going to factor out the common terms. And for numbers, that's not so bad. But what do you do with powers? So the rule of thumb is always pull out the lowest power. And that, if you follow that rule, it will get you very far. So what do we have? Well, what's the lowest power? Well, is it -1 or is it -3? And in this case, the answer is -3, because -3, if you think about it as a number line, -3 is below -1. So we're going to pull out x and -3. All right, what else should we pull out? Well, they all have a factor of 4, so pull out a factor of 4, and they all have, well, there's a 3 downstairs. This one doesn't have a 3. But I think if we pull out a 3, that would be good, because we'd like to have things that are left look like integers. Now, what's left? Well, we grab the 4/3 out of the first term. Here we have x to -1. We pulled out x to -3. Now, this is when we really test. We understand what happened. So what do we end up with? Well, one way to figure it out is to sort of say, what would this have to be? So I ended up with x to -1. And in this case, I say, well, if I'm going to subtract 3, it better be x squared. Because if we think about it, x to -3 times x to the 2, their exponents would combine to give -1. All right. Another way to see it is you take -1 and you subtract -3. So you subtract the power you pulled out. So the next term, well, that will be plus 2, and now we'll have an x. The last term, notice we have the minus, so that'll be a minus. We grab the 4, but there wasn't a 3. So what do we do about that? Well, the answer is we put a 3 there. So you can check 4/3 times 3 will give us 4. And the power is just 1. All right, now, can we find something to simplify this even further? We need to have two numbers who multiply together to give -3 and add together to give 2. What does that? The answer is, do you see it? It's x plus 3 times x minus 1. All right, and there you go. That's the kind of manipulation that you might encounter. Now, we actually did something up here, which was that we were working with powers. We said, oh, look, you combine powers together. So let's write down some basic rules. If you have x to the a times x to the b, that's the same as x to the a plus b. Or if you have x to the a divided by x to the b, in other words, you have a power upstairs or downstairs, that's x to the a minus b. That's essentially what we used when we said, hey, this x squared becomes x to the -2. The other thing we need to note is that x to the a raised to the b is x to the ab. Now, we should note this is really about manipulation of exponents. So it doesn't have to be an x downstairs. It could be, say, e. Now, e is a very famous number. Now, what is e? Well, e is the number, it's approximately 2.71828. And, well, that's a kind of a weird choice for a number. But it has some beautiful properties. And we're going to talk about some of those properties in calculus. But again, I can manipulate those expressions like we have there. So essentially, you should think of e, this is approximately 2.71828, and you can remember it by a chant that goes, come on, exponentiate 2.71828, wah! Exactly, good. Now, so what do we have? This is exponentiation. Now, is there something that is the opposite of exponentiation? And the answer is yes, logarithms. So normally we use ln. This stands for natural log. And it's the opposite of exponentiation. In other words, it undoes what exponentiation does. All right, well, why should we care? Well, the beautiful thing is that rules for exponents transform very nicely into rules for logarithms. So what are some nice things to know about logs? So for instance, this rule becomes the fact that if I have multiplication happening inside a log, I can break it up into addition. So that's a nice fact. It allows us to pull things apart. This rule here tells us if we have division, it becomes subtraction. And this rule says if I have a to the b, I can bring the b down. That's b log of a. Now, why do we care about logs? Well, logs are really, really nice because it takes things which are products and powers of crazy expressions, and we say, apply a log, one log, and then we can pull it apart, pull it apart, pull it apart. And so this gives us a way to break things into oftentimes simpler pieces. In fact, there's a nice technique in calculus called logarithmic differentiation, which is based off this idea. Now you might say, okay, how about log of a plus b? What does that become? All right, good question. The answer is log of a plus b. It doesn't simplify. And what you're seeing here is that there's this interplay between addition and multiplication. Because when we talk about exponentiation, it's really a variation of multiplication. And they don't always mix together. So you got to be careful. One of the things is you have to know the rules, but also know what's not a rule. What doesn't change? What doesn't simplify? You need to know. Inquiring minds want to know. It's good to know these things. All right. Well, let's talk about solving. So when we talk about solving, what we really mean is solving a system of equations. Now, what tools do we have for solving? There are three main tools. One of the main tools is factoring. Another one is substitution. And our final one is combinations. So in other words, combining things together in a nice way. So let's try this out. Let's try to solve a problem. Okay, so here we go. First example. Suppose I want to find all values of t where t e to the t plus 2t minus e to the t is equal to 2. All right. Now, our first reaction is, what? Is that possible? Can it be done? And our second reaction is, cool, let's do it. Okay, well, what are we going to do? Well, we're going to try this with factoring first. Now, how does factoring work? Well, the key to factoring is you want to have stuff equaling 0. So this 2 is not good. We don't want it equal to 2. We want it equal to 0. And we'll talk about that in just a second about why. So it's okay to move it across. So we just do the same thing to both sides. So if I want to get rid of this 2 here, I would subtract 2. So I subtract 2 from both sides. Equals 0. All right, now what? Well, we're looking for factoring. So one of the things you can do is if you're looking for factoring is you can say, okay, is there any nice way to sort of put things into chunks? And say maybe that we can chunk things so that the pieces factor. So for instance, let's look at the first 2 terms. They both have a t in common. So I could pull that out. And that'll give us e to the t plus 2. And I say, oh wait, e to the t plus 2 looks a lot like this. In fact, if you just pull out a minus, that's also e to the t plus 2. And then we say, look, now these pieces both have e to the t plus 2. Let's pull that out. And we can pull it out on either side. I'll pull it out on the end. T minus 1 times e to the t plus 2 equals 0. Now what do we see here? Well, we have 2 terms which multiply together give 0. And at this point we were like, wow, wow, this is so cool. Why? Well, 0 is magical. Beautiful number. What's special about 0? Well, it turns out if you have stuff which multiplies together and you get 0 at the end, what had to be the case is something had to be 0. So we know we multiply these together, we get 0. That says, hey, either this term is 0 or that term is 0. Now it's not that they both have to be 0, just one of them does. So this says that, well, t minus 1 equals 0, or e to the t plus 2 equals 0. All right, well, what does that say? Well, here, we can say this says t equals 1, or e to the t is negative 2. So t equals 1, that's a solution. How about e to the t equals negative 2? Well, it turns out, what has to be true? Well, can e to something ever be negative? And the answer is no. This is impossible. So that means that this one actually only has one solution, t equals 1. So it is possible that maybe you get one solution, maybe you get more than one solution. All right, good, good. Now, on a side note, 0 really is this magical number. And so if you ever have things that multiplication and you get 0, then this implies that at least one term is 0. Now, that's tremendous. Great power, great power. And of course, as they say, with great power comes great responsibility. All right, let's do another example. Suppose this one's a fun one. xy minus x plus 2y minus 2 equals 0, and x squared plus 5x plus 4y equals 0. All right, what can we do? Well, now we don't have one equation, we actually have two equations. Two equations, two things we don't know. So we're going to have to work, I guess, twice as hard? Maybe. Probably a little bit harder. I don't know if we have to work twice as hard. Well, there's a couple of things we can do. So one thing we can do is we can try factoring again. And I like to try factoring. I think factoring is powerful. Another option is substitution, which is, notice in the second equation there's only a single y. So we could solve for y in this equation and substitute up here. But if we did that, we'd get a cubic, and cubics are hard. Cubics are hard. So let's just try to solve by factoring first. So here we go. What do we get? Well, we get x times y minus 1 plus 2 times y minus 1 equals 0. Again, I'm just sort of working in chunks, which becomes x plus 2 times y minus 1 equals 0, which means either x equals negative 2 or y equals 1. Again, using our beautiful fact that one of those has to be 0. Now notice it's not, it's the point x equals negative 2 comma 1. They don't both have to be 0 at the same time. So what do we do now? Well, we say, hey, wait a second. We only used one equation. We have this other equation here we haven't touched yet. So what we do is we now plug in our possibilities. So suppose we plug in x equals negative 2. That would give us 4 minus 10 plus 4y equals 0, which becomes 4y equals 6, or y equals 3 halves. The other option is we plug in y equals 1. That would give us x squared plus 5x plus 4 equals 0, which becomes x plus 4 times x plus 1, because we can factor, which tells us that x equals negative 4. Whoops, it's supposed to be negative 4 and negative 1. Now we get points because we have an x-y pair, so negative 2, 3 halves. And we also have an xy pair, negative 4, 1, and negative 1, 1. So 3 different answers. Cool, cool. Now, let's pause for a second and say, well, what if we'd done something along the lines of the following? Suppose we had come up here and said at the start, maybe this is xy minus x is equal to minus 2y plus 2. So in other words, I moved some terms across, and then we said, hey, well that's x times y minus 1, and then this is negative 2 times y minus 1, and then we said, oh, the y minus 1 is in common, so we cancel it out. So that would say, well, x is negative 2. Now at this point you should say, well, okay, so I'll get the point negative 2, 3 halves. But what happened here? Remember, we said that 0 is powerful. And so with this great power comes great responsibility. And here, what's the danger? Y minus 1, maybe that was 0. So remember, don't divide to cancel unless you are 100% it's not 0. Because if it is 0 and you cancel it out, you lose solutions. But here's the good thing. If you can divide to cancel, you can also bring everything to one side and factor. So cancellation can be replaced by factoring. All right. Well, what's something else we can do? Well, let's try another system. Let me try a different color here. This is blue color. Suppose we have 3x plus 2y equals 1. And also 4x plus 3y equals 6. Now, what can we do? Well, one of the things we can do is we can do substitution. We haven't done that yet, so let's do an example. We can solve for one of the variables. So let's say we solve for y. 2y is 1 minus 3x, which tells us that y is 1 minus 3x over 2. Now that we solve for y, we can plug it into the other equation. So this is substitution. Solve for one variable, plug it into the other. So we get 4x plus 3, then we have 1 minus 3x over 2 equals 6. All right. Well, probably fractions are not fun. So let's just multiply everything by 2 to get rid of the fractions. 8x plus 3 times 1 minus 3x equals 12. So everything got multiplied by 2. Now this becomes 8x plus 3 minus 9x, because the 3 distributes through, equals 12. And then what do we have? Well, we have 8x minus 9x, which is minus x. So this becomes 3 minus x equals 12. Or I can move the minus x across, move the 12 across. X equals 3 minus 12, which is negative 9. Now, that tells us that our solution is, it has x needs to be negative 9. So our point would be negative 9, comma. Well, what's y? To find y, we come back here. So that would be 1 minus 3 times negative 9 over 2. So 1 plus 27 is 28 divided by 2. That would be 14. Good. Now, one of the things you can always do is after you've done a problem, you can check. So here we can say, well, okay, let's check. 3 times negative 9 is negative 27. 2 times 14 is 28. Negative 27 plus 28 is 1. Good. 4 times negative 9 is negative 36. 3 times 14 is 42. The answer to life, the universe, everything. Negative 36 plus 42 is positive 6. Now what haven't we talked about? Well, we haven't yet really talked about combination. Now combination can oftentimes take the place of substitution. So let's just give an example with this last equation here. So we're going to come back to this equation. So where we have 3x plus 2y equaling 1 and 4x plus 3y equals 6. The goal is how can we put things together to come up with a nice equation. So what I want to do is I want to combine these two equations in a way to cancel something off. Let's suppose I want to cancel the x's. So I want to find something that would multiply one equation. I want to multiply the first equation by something, the second equation by something, and then add them up and cancel off. So I can multiply the first equation by, let's say, negative 4, and the second equation by positive 3. So I'm taking a combination of equations, and I have to do it to both sides. So negative 12x plus 12x makes 0x. Negative 8y plus 9y makes y. Negative 4 plus 18 makes 14, which tells us y better be 14. Cool. And now that you know y, you can go back to one of your original equations. Doesn't matter which one. Let's say we plug it into there. We can say 3x plus 2 times 14. That would be plus 28 equals 1. So 3x equals negative 27. And so x equals negative 9. And so there we go. Negative 9, 14, the same as before. So this is another method that you have when you're working with systems, particularly when you're working with linear systems. So linear means that there's nothing, they're all first powers, easy to work with. Essentially means you're working with lines. Notice that some systems aren't linear, like that x squared, which means you got to be a little bit more careful. Or, as the saying goes, you need to do a little bit more work. But that's okay. We don't mind doing a little bit more work. All right, well, let's try something a little different, not too different. Suppose you have the following. Suppose you want to solve e to the 2t minus 3e to the t plus 2 equals 0. And that was our problem. What can we do? Do we have the tools to solve this problem? And the answer is yes. Yes, we do. So one of the things that we need to recognize is there's lots of ways to write things. So e to the 2t can be written as e to the t squared minus 3 e to the t and plus 2 equals 0. So here's a very important idea. Changing our names. And what does that mean? Well, we're going to change what we call things. So instead of calling this e to the t, we're going to call it x. So x is now e to the t. What does this become? X squared minus 3x plus 2 equals 0. And now if we write it like that, we say, hey, wait a second. This is a factoring problem. I'm great at factoring problems. Now you might say, but are we allowed to change names? Yeah! In fact, changing names is one of the most beautiful and most important ideas in mathematics. And the sooner you get used to that idea, it's like, oh, okay, let me just change what I call things, the better you'll be. So this becomes x minus 1 times x minus 2 equals 0. Or, now going back to our old names, e to the t minus 1 times e to the t minus 2 equals 0. So which says that e to the t has to equal 1, or e to the t better equal 2. So this happens, e to the t equals 1, that's at t equals 0. And e to the t equals 2, that's at t equals log 2. Now t equals 0, how do we know that? Well, there's some simple facts. E to the 0 is 1. And this is related to the fact that log of 1 is equal to 0. Of course, e to the 1 is e, which is related to the fact that log of e equals 1. That's not very surprising. And in general, we say, well, suppose I want e to the t equals 2. I want to get that t outside of the e. Now, how do I do that? Well, I don't divide by e because I'm not canceling this value e. I have to undo this exponentiation function. So we do that by the thing that undoes the function. But if we do it to one side, we have to do it to the other side. We have to be careful to make sure we do it to the whole expression of both sides. And log of e to the t, by our properties, is t. So that's how we get t equals log 2. All right, good. Now we come to one of our most important topics. And that is the following. We're going to draw our grid, sometimes say the plane, the x, y plane. And we're going to talk about lines. Lines are flat, and flat is good. Good things, because we understand flat things. Flat things are the part of mathematics that we understand the best. So anytime we can use a flat object to understand things, we do use that flat object. Now, how do we describe a line? Lines almost always have two things involved. One is a point, and what does this give us? It really gives us a location. It nails down the line in space. And the other thing that we have is a slope. And this tells us the direction the line goes. Now, a slope, that's really a rate of change. How much are we changing? In other words, we can think of it as the change in y over change in x. So how much is the y value change as we move in an x direction? So in particular, change in x is how much we move in the x direction, and change in y is how much we move in the y direction. Sometimes we call this our m. Now, if you have a line, what are some ways to write it? Well, there's two common ways. Y equals mx plus b, where m is your slope and b is your intercept. And by the intercept, we mean where you hit the y-axis. Now, the other way to write your line is y minus y naught equals m x minus x naught, where m is again your slope and x naught y naught, this is a point on the line. So maybe there's a point here, x naught y naught. So when you're looking for lines, almost always the easy thing to do is the point. The point's almost always given to you. The hard thing is the slope. And so we have to figure that out. In fact, the first part of calculus is, how do we find the slope that we need? So let's do a quick example. Let's find a line that goes through 2 points. Well, which 2 points? I don't know. Let's say 2, 1 and 4, 5. So what do? Well, let's find our slope, and that's our change in y. So 5 minus 1 over our change in x. 4 minus 2, in other words, I take the difference in the y's, difference in the x's, and so upstairs we get 4, downstairs we get 2, also known as 2. Now we have our slope. And we have points, so we say, all right, we can write this as y minus, pick a point, doesn't matter which one. Let's say our first point. Y minus 1 is 2, x minus 2. And there you go. Now if you wanted to, you could continue to manipulate it. So for example, I could say y minus 1 is 2x minus 4. And I can add 1 to both sides, so y minus 1 is 2x minus 3. Oops. Y equals 2x minus 3. Got a little excited there at the end. Okay, so there you go. Now you can find a line. All right. So, one more basic thing we should talk about, and that is we should be familiar with some basic pictures that we'll see from time to time. These are sort of the important graphs that show up again and again, so we should know what they look like. So we're going to sketch maybe about a half dozen. Okay, so let's put some grids here. And we'll put some grids here. All right, so what are our curves? Well, let's start off with a really easy one. Y equals x. That's not so bad. That's pretty straightforward. The next one, parabola. We're going to see parabolas are great examples we're going to keep seeing over and over again. So we should get used to our parabolas. Y equals x squared. Now related to this, y equals x, let's talk about the curve y equals 1 over x. Now let's think about what's happening. So if I have an expression like 1 over x, when x is a large value, 1 over x is small, so it should be small towards the ends. On the other hand, if x is small, 1 over x will be big. So it should be very large. And now we have to pay attention to the sign. So notice here, I'm negative to the left and positive to the right. So when we sketch 1 over x, it's going to be a very large positive value when x is positive, going to a small positive value, and a small, very large negative going to a small negative. So that's the curve y equals 1 over x. So they go sort of 2 different ways. Now y equals x squared, a little bit different in that they're going to go to the same up. So this together. This is y equals 1 over x squared. All right. Another thing we should note here other functions, is our exponential function, y equals e to the x. This is an important function, and it looks like the following. It's going to intercept here at 1, and then it's going to go up. So as x gets large, positive, e to the x gets huge. On the other hand, as we go in the other direction, large negative values of x, e to the x is going to get very, very small, get tiny. Now the opposite of e to the x, or really the inverse function of e to the x, is logarithm. And so it's going to come up and do this. So it's going to cross here at 1. So this is y equals natural log of x. Now you'll notice that there's a couple of important things. First off, e to the x is always positive. It never hits 0 and it's never negative. Y equals log x only works if you're positive. And the other thing, of course, which you should note, is if you took the line y equals x and you were to flip across the line, what you would see is that e to the x becomes log of x. And that's not a coincidence. What you're seeing there is that they're inverses of each other. So inverses, they relate by this flipping. So in other words, if I'm at a point a, f of a, and I flip, then that's going to go to a point f of a, comma a. So in other words, I'm changing inputs and outputs. So that's what will happen there. All right, a couple of final notes here. Let's talk about what happens when we do some manipulations. So suppose I take the graph y equals f of x. If I add f of x plus a, notice that this is affecting the output of a. So what does that mean? Well, if I'm affecting outputs, I'm affecting the y values. So this is a vertical shift. In other words, I'll move it up and down. On the other hand, if I had y equals f of x minus a, and this minus, you have to be a little bit careful of it. See, the inside does the opposite. So vertical shift, if I say, plus 2, okay, on the outside it moves up by 2. If I have plus 2 on the inside, it actually moves left by 2. So you got to pay attention. So this affects input, so that's a horizontal thing. So this is a horizontal shift. Now, of course, I can do other things. So for example, I can do a f of x, and this is a vertical stretch. Of course, you might have a be negative, which flips the whole thing over. You might also have a be a small number, like a half. That's a vertical shrink. So, but stretched by a strange amount. And of course, you could also do the same thing on the inside. This is a horizontal stretch. And another thing that happens with functions is symmetry. So what do we have? Well, you might have the following. F of negative x is the same as f of positive x. So in other words, the graph is doing something where whatever you plug in here, it's the same thing you would get plugged in there. Examples, y equals x squared, and y equals 1 over x squared. These are both functions which have this property. We call these even functions. And what do you notice? Here, 2 is an even power. Even functions are even powers. You might say, okay, well, what about the other case? What if we have an odd power? Like here's x, that's odd, that's x to the 1. 1 over x, I can think it says x to the negative 1, that's also odd. Well, okay, these also have symmetry. What's their symmetry? Well, their symmetry is if you plug in negative x, you get negative f of x. They're called odd functions, and they have a shape that looks like this. And these have beautiful properties as well. All right. Well, we talked about a lot, but hopefully you know this all. I mean, it's algebra. These are the skills that you'll need. And I'll tell you, as you do more calculus, you're going to get a lot better at algebra, because you're going to do a lot of practice of solving and manipulation. Now, one thing we haven't talked about yet, and we haven't for a very good reason, is that there's a cardinal sin. Now, let's do a very special case. A plus b squared. That is not a squared plus b squared. Remember, when we squared out, there'd have to be an extra term in the middle, 2ab. That's because multiplication and addition aren't the same thing, so we have to be careful when we mix the two together. Now, why do I mention this? Well, if I have a squared plus b squared to the 1/2 power, or some people like that as the square root of a squared plus b squared, you might say, you know what would be great is if I could just take the square root of each. In other words, a plus b, because square root of a squared, square root of b squared. But these are not the same. Again, addition, this plus in the middle, doesn't mix well with exponentiation or multiplication. So be careful. Be smart. Don't make this mistake. You know, at the very least, don't do that one. And preferably, don't do any. And how do you not do any? You practice. Practice. The more you practice, the better you get. All right. Well, good luck.